Lab 4. In this fourth video lab report, we analyze the motion of an object of known mass hanging from a spring, creating an assimilation with a man hanging from a rope. We were able to make this comparison because of the similarity in structure of a rope and a spring. First, we analyzed the video of the object's motion in order to get the x and y positions, to then create a computational model that could predict the motion using Newton's second law. The lab consisted of two parts. First, only Newton's second law was used to predict the motion, and so the system was composed by the object only, while the surroundings included the earth and the spring. For the second part, the energy principle was used, and the system was now composed by the object, the earth, and the spring. Having no surroundings means having the difference in energy be equal to zero, this being said by the energy principle. Further details about the procedure and results will be given throughout the video, but it's important to mention that the results prove that both the predictions and the observations are very similar, and that delta E is actually equal to zero. As mentioned earlier, the first part of the experiment consisted of creating a computational model that could use Newton's second law to predict the motion of the object hanging from the spring and being pulled by the force exerted by the earth, the weight. In the second part of the lab, the energy principle was incorporated to the prediction model. Let's start by looking at the analysis done on tracker. The calibration stick is set up to be 0.70 meters, measuring from the fixed point to the center of the object, on the moment when the object is grabbed before being released. The time frame used in the video is 10.5 frames per second. The positive axis points to the right, and the positive y-axis points to the top. After selecting the point of mass at each frame, the positions at x and y are obtained and copied into a CSV file to later use them in the code used to complete the prediction. In terms of time, we won't play the video on tracker. After having analyzed the object in tracker, let's take a look at the Python code. The initial conditions used in the code include the mass of the object, which is 0.402 kilograms, the initial position of the object obtained from tracker, the initial velocity of the object, which is 0 since it starts from rest, and the start counting time, which is equal to 0. Next, we determined certain parameters that will later be used in the loop. The first parameter is the gravity constant on Earth, which is equal to 9.8 meters per second squared. The next parameter is the stiffness constant, which was obtained using the period of oscillation formula. Knowing the average time of the period of oscillation, which is 1.524 seconds, and the mass of the object, which is 0.402 kilograms, the stiffness constant can be obtained, and it is equal to 6.83 newtons per meter. The next parameter is the relaxed length, which can be obtained at a point where the object is at rest. If the object and the system are at equilibrium, we know that the sum of the forces acting on the system equals 0. From there, we can equal the weight force, which is equal to mass times g, to the force from the spring. Finally, having this equation established, we can solve for the relaxed length, which is equal to 0.123 meters. The forces and then the energies are established in the while loop to create the prediction in the model. When using Newton's second law only, our model prints the graph comparing the y position versus time, and then to print out the x position versus time. When applying the energy principle and writing all the energies, our model prints a graph of all the energies from the system and the total change in energy being equal to 0 for the mentioned fact that the system is composed by all of them, the object, the spring, and the earth. Delta UG gravitational potential is the green graph. Delta US spring potential is the red graph. Delta K kinetic energy is the blue graph. And finally, the total change in energy is the yellow graph, which is at 0, as you can see. Then the graphs are printed out, including the y position and the x position using the energy principle. Let's run the code to see the spring's motion. As you can see, the arrows point at the spring force and the gravity force. Let's now take a look at the graph comparing the predictions with the observations from the code that uses Newton's second law only, and then for the code that is applying the energy principle. As you can see, the predictions are very close to the comparisons. Answering the first discussion question, the energy principle is satisfied by our models because the total change in energy from our model is equal to 0, and it should be equal to 0 since we know that there is no surroundings acting on the system. The system is composed by all the spring, the earth, and the object itself. Answering the second discussion question, the two estimates of oscillation periods using the x position and the y position are very similar for the fact that the periods won't change although we might use x or y. Also, Estimating an average means that both x and y positions of the oscillations will be pretty much the same. To conclude, it's important to mention again that the results show that the predictions are very similar to the observations. The parameters used did let us create the prediction of the motion of an object hanging from a spring. Thank you.